extra.
Yep.
Could I get my test back?
Yes, it's right there. One of them. So I think it's, you guys are this kind. Okay, thank you. Yeah, 417 people, if you want to come by. So I already gave back some of the exams on Monday. If you want to come up and get your exams out, you can. Sorry, need to actually download some stuff.
So they're going to be a MATLAB day?
I'm going to show you MATLAB codes, but there's nothing for you to actually code in them. So it's more of just a demonstration.
Okay.
Yeah. Not too big. Hey, Jacob.
Can I take my exam?
Normally I give him. Yeah.
I can wait.
Yeah, I'll do that. We'll do it after class.
Okay.
Just so everyone gets at the same time. We have faculty meeting 2 weeks in a row. We have a meeting tomorrow and a meeting next week.
So one of those where it could have just been me.
It could have been a Zoom call, that's for sure. For next week, we have a special guest, DEI Professional Development. I have no idea what the hell that means. Whatever.
Oh, yeah, yeah, yeah. Yeah, yeah.
Any plans for the weekend?
Go see my parents this weekend.
Nice.
That'd be nice. I haven't seen them in a while, so
Nice.
I'm gonna get dinner. How about you?
Just working on schoolwork. That's all I can really do, man.
It's a grind, that's for
Yeah,
sure.
Just halfway there.
Yep. June 16th? No. That's way too late. I think our last day of class is like May, somewhere middle of May. Yeah.
May 11?
Yeah.
13?
Yeah, May 11th to 13th or something like that. Yeah, June 16th is for quarter system schools, I think. But they also start a lot later than we do. Okay, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Hanging in there? Yeah, I know it's a grind. So I always teach a lot of I mean just because of the class that I teach. I end up teaching a lot of seniors and grad students around this time, and so I know the look on everyone's faces right now is pretty typical of this time. So I know it's a grind. I know it's you guys have a ton of stuff going on, but just hang in there. All right, and so the plan for today is we're going to finish up our set of lecture notes on time marching schemes. And so I have just a couple more examples I want to show you for that. And then with that, we'll actually wrap up the first half of the class on finite difference methods. And so we're going to transition then to the second half of the class, which is based on a different method called finite volume. So this class is pretty interesting, actually, because it kind of has it's a tale of two halves, actually. And so what you'll see in that finite volumes, we're solving the exact same problems, and for some cases we'll end up with almost the exact same thing. But finite volume is actually a different method that we can use to solve these kinds of equations. Okay, in a lot of cases they end up being pretty similar, but then there are some key parts where they're actually different. And so, and so we go over both in this class, which I think is kind of a cool thing to see. All right. Right, and so the other announcement I have is, remember homework 4 is out there, and so make sure you're working on that. And so that's due next Friday, okay, before the break. And I know there was an issue with the PDF not being uploaded and the video is not loading, and so I've updated the PDF so that it works there. And the videos I don't think are working on Canvas, but I uploaded them onto Discord instead. And so if you're curious about what your solutions for 3A and 3B are for the homework, you can check out the videos that I've uploaded onto Discord. Okay. Okay, and so that's all my announcements. And so are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick up where we left off. And so I think at the end of last class, we were kind of rushing a little bit to get through this example, but I wanted to take my time and kind of go over the whole thing again. Okay. And so the idea with this example is that we have a vibrating string. And so we have a simple kind of unsteady diffusion equation. Okay. We had partial phi partial t is equal to 3, partial squared phi partial x squared. Okay. And so we don't have any convection. We just have pure diffusion with an unsteady term. Okay. So that's not too different than what we've been covering for the last couple of weeks. But where it is different is right here. Okay. And so the big difference that we're seeing here is that instead of a boundary condition that is constant with time, we now have a boundary condition that is changing with time. Okay. And so in terms of the algebraic equations that you would write out by hand, not much is going to change, but we do have some implementation differences in MATLAB. Okay. And the primary difference is the addition of a time variable. Okay. And so what you'll see in the code is that we're going to be keeping a time variable that we need to use to update this boundary condition. Okay. And so I think we did go over briefly the code last time, but I wanted to work it out by hand, just so that you can kind of see clearly, what the differences are and why we need to make differences in our code. Okay. Okay. And so from that problem, we are going to use the implicit Euler. Okay. And so that's the scheme we're going to use to march the system forward in time. And we're also going to use a simple grid of 5 points, our favorite 5-point grid. To run the simulation. And so here is our domain. Okay. So we have 1, 2, 3, 4, 5. Okay. And we're going to assume the grid spacing is going to be 0.25. And we're going to assume the time step size is 0.1. Okay. And so through the implementation of these methods, on this domain, we're going to end up with a set of 5 algebraic equations. Okay. That are going to be marched forward in time. Okay. All right, so let's start with the interior nodes. Okay, so let's start with the nodes that are here. Okay. And so for the interior nodes, we know that we can apply our direct kind of implicit Euler finite difference scheme for that. Okay. Okay. And so we have an expression, and so we have a formula for this. Okay. And so I'm just going to end up plugging the formula, but we end up with this formula right here. So we have minus 4.8 b I minus 1 with the time index of n plus 1. Okay. Plus 10.6 bi n plus 1 minus 4.8 bi plus 1 n plus 1 is equal to phi n. Okay. Okay. And so if you look back in your notes from the previous weeks and you look at the section for implicit Euler, this is basically the result of plugging into that expression. Okay. And so into that expression, of course, you're going to need to plug in the grid spacing. You're going to implement the time step size. You also need to plug in the diffusion coefficient. So the diffusion coefficient is 3. And then our convection velocity, since we don't have any convection here, is just set to 0. Okay. And so you plug in all those numbers into that expression, then you get the following, update equation. Okay? And so let's apply this equation to nodes 2, 3, and 4. Okay. And so we apply it to node 2, and what we get is minus 4.8 V1 n plus 1 plus 10.6 V2 n plus 1 minus 4.8 V3 n plus 1 is equal to V2 at n. Okay. Okay. For node 3, we have a minus 4.8 V2 at n plus 1 plus 10.6 V3 n plus 1 minus 4.8 V4 n plus 1 is equal to V3 at n. Okay, and then we have the same thing for node 4. Okay. All right, so that's three out of 5 equations that we have. Okay. Now let's do the equations for nodes 1 and 5. And so of course these are going to correspond to our boundary conditions. And so let's start with the left side. Okay. And so we scroll back up to the problem here. You can see on the left side we have a Dirichlet boundary condition, but it's a function of time. Okay. And so the way that we can implement that oh, thank you. Yeah, so it should, on the right-hand side here, it should just be n, not n plus 1. Yeah, sorry about that. Okay. And so for the Dirichlet boundary condition in node 1, right, we can say that phi1, and we'll say that this is at n plus 1, is equal to cosine of pi Tn. Okay. And then similarly, we're going to have a Neumann boundary condition on node 5. Okay. And we know that the equation for this is going to be phi5 minus phi4, both at n plus 1, is going to be equal to 2 times delta x. Okay. And since delta x here is 0.25, this is going to be equal to 0.5. Okay. All right. And so boundary conditions are fairly standard, except, of course, the Dirichlet boundary condition is going to be the cosine function. Okay. And so just so that you can see it all together in one place, let's put this in matrix form. Right? Because remember, for implicit schemes, we have a system that looks like this. Okay. And so we have A times phi I n plus 1 is equal to B. Okay, where B is kind of everything on the right-hand side here, right? So let's put that system together. And so let's start with our matrix A. Okay. And so our matrix A, we have a 1, 0, 0, 0, 0.
Question.
Yep.
Going back to the for now the equation.
Yep.
The Tn.
Mhm.
Is that just going from like 0, 1, 2, 3?
Right. So the Tn here takes the notion of the time step size into account. So remember, the time step size is 0.1. And so when we solve this for the first time step, we have, well, first of all, we have T0 is equal to 0 because we start then. And so when we move on to the first time step, T1 is just going to be 0.1. and then T2 is going to be 0.2. And so that Tn is that time variable that I mentioned before that we have to keep track of in the code. Yeah, you'll see that implemented. And so it's basically another variable that we have to keep track of that keeps track of what the current time is. And then we have to use that in our equations.
That was that little code that you were referring to earlier.
Exactly. Yeah. So we'll go over it again just so you can see, because I know it was kind of fast at the end of class last time. Okay. And so that's the first row. Next, we have a minus 4.8, 10.6, minus 4.8, 0, 0. Okay. And so those are our coefficients on the left-hand side. Okay. And on the right-hand side, for the first entry, we have our Dirichlet value, which is cosine of pi Tn. Okay. Then for all the interior nodes, we have to include the solution at the previous time step or the current time step. Okay. And so that's phi2 at n, phi3 at n, phi4 at n. Okay. Remember, since we already know what the solution looks like at the current time step, we can plug those in on the right. Okay. And then for the Neumann boundary condition, we just plug in 0.5 force Neumann value. Okay. And so remember, everything here is known. Okay. If it were unknown, it would have to go on the left-hand side of the equation. But since they're all knowns, then we stick them all on the right. Okay. And so what we have right here is a pretty classical, time advancement equation setup for implicit Euler. Okay. And so in order to solve for, remember, we're solving the system for all of these guys. Okay. Right. In order to properly solve the system for all of this, we have to take our matrix here and invert it on the other side. Okay. The only difference here is that the right-hand side equation right here needs to be updated for every time step. Okay. And there's two main places where it needs to be updated. So first of all, we have to update the current solution for new values of the current solution. Okay. And so rows 2, 3, and 4, we have to update those with whatever we solved for last. Okay. And so that's not new. And so we've had to do that, for all the other cases as well. But what's different here is that we also have to update the value of the boundary condition as well. Okay. And what you'll see in the code is the code's going to update based on that. Okay. All right. Any questions on this before we jump into the MATLAB? Okay. All right. So I think we saw this code last time for a bit, but I did want to show it again. Just to be a bit clear. I don't think it's this one. It's this one. Okay. And so first thing you should see here is that so this is not like a really complete code. This is kind of just like a test case. And so don't use this for your homeworks and stuff. But I did want to illustrate how this code works. Right? So first thing you can see here is I'm defining the coefficient matrix. And if you look at the coefficients of this matrix, they should match up with what we just wrote down for the example. Okay, so we have 1 in the top left, 1 on the bottom right, and all the minus 4.8s and 10.6s. Okay. Next, we have to define the excuse me, the forcing vector. Okay. Right, so this is all the vectors on the previous side. And so first we create the space for it. And so we say that B is a zeros vector with 5 rows and 1 column. Okay. And what we say is that the last entry in this vector is 0.5 and the first entry is 1. Okay. And the reason I set the first entry to 1 is because, we're starting at time 0, right? So t is equal to 0 at the beginning. And so when we take cosine of 0, that equals to 1. And so I just kind of did a shorthand there. Okay. All right. And so next, also very standard with, with our, with our unsteady problems, we have to define a variable that carries the next solution. And so this is phi n plus 1, this sol next. Then we create a variable to carry the current solution. And so this is phi at n. Okay. And then after that, we enter the time step loop. So actually, let me do this. And so, I think this is the first time we've seen a while loop here. And I don't know why I do this, but let's look at the for loop version of this code. Let me go ahead and comment that out. And let's look at this. Okay, so here is the for loop version of the code. And so you can see here that I have a for loop where we loop from 1 to nt, where nt is the number of time steps that we're solving for. Okay. And you can see right here what I'm doing is I'm updating the forcing vector, right? And so just like we just wrote down, one thing that's going to be different here is we have to update our forcing vector. And so we said that b at 1 is equal to cosine of pi t, right? Where t is a variable that we'll go over in a second. Okay. And then b2, b3, b4, these are all the current solution. And so this is phi 2 at n, sol cur 3 is phi 3 at n, and sol cur at 4 is phi 4 at n. Okay. All right, so now that we have the coefficient matrix satisfied and we have the forcing vector satisfied, we can go ahead and invert the system. And so in order to solve for phi n plus 1, we take the coefficient matrix and we invert it and we multiply it by b. And so that's what our backslash does. And then we update our current solution. So once we solve for the next solution, then our current solution becomes that. Okay. And this code right here is just concerned with plotting, and so you don't have to worry about that. Okay. Okay. And so we have to do one more thing, because usually after we update the solution, we should be done at this point. But because we have a time variable that we need to keep track of, right? This cosine term has this time. We have to update that time variable in order to have the correct value. Okay. And so what I'm doing here is I'm taking t and I'm just adding to it the time step size. So t is equal to dt, or t is equal to t plus dt. Okay. So each time that we run through the loop, the t value gets incremented by 1. Okay. Or not by 1, by 0. Excuse me. Because dt here, dt is equal to 0. Okay. So this part's really important. And so when you have terms in your problem that depend on t, then you need to make sure that you keep a time variable and you update it appropriately. And so in this problem, we have a boundary condition that changes with time. But the next example, we're going to look at a case where the convection velocities actually change with time. Okay. All right. So any questions on this code here? Okay. All right. So I'm going to go ahead and run it one more time. And so what you'll see is that when I run it, it's going to end up being a wiggly string. Okay. It's a little choppy right now because it's still being solved. I hope the next code can solve, but the next code is actually a lot more expensive than this one. But it's already kind of dying right here. Okay. Okay. So let's go look at the video. Okay. So you can see here we have an oscillating string. And again, pay attention to what's happening over here, right? And remember, over here, what's happening is that that boundary condition is changing as a cosine function, right? So it's kind of going up and down. And as that boundary condition goes up and down, then the solution at the rest of the domain kind of reacts to it accordingly. Okay. So we'll play one more time. It's kind of cool to look at. Okay. Okay. And there's your solution. And so, now we're, with this set of lecture notes and what you'll see in the next example, we're really utilizing the power of these unsteady schemes, because we can actually simulate unsteady phenomena. Okay. And this methodology will be a big part of your final project too, because your final project, we're going to have an unsteady situation, and you're going to be forming videos for your solution. And so whether you choose to use finite differences or finite volumes for your final project, this part is going to be really important. All right, any questions on this before we move on to the next example?
Just kind of for like clarification. So you could have put that boundary condition at node 3, and then we would have seen that like in the middle reacting that way.
Oh, sure, yeah. If you wanted to have the boundary condition at in the middle of the domain and have that be your Dirichlet value, then you can have that as well. Yeah. Typically it's at the edges though, because that's where you're usually not able to apply an interior equation at the end, and so usually it's at the end.
It was just more for like understanding the graph.
Oh, okay, I see. Yeah.
Thank you.
Our question. So what happens when the B5 value goes up or down? Yeah. So the B5 value, the reason you see it going up and down is because it's basically reacting to what the other boundary condition is doing. And so that's a good question actually, because from the problem, it might seem like the the condition at the right, it shouldn't be changing with time, because we're implying, or we're specifying a constant boundary condition there, right? But you can see from the video that it actually is changing its value up and down. And so remember, the boundary condition we're applying on the right is not a Dirichlet boundary condition, but it's a Neumann boundary condition. And so what we're saying is that the slope here is going to be constant, but then we don't really say anything about the value. And so because of that, the string at the right here can also change up and down. But if you notice the slope of the line at the end right here, it's approximately constant. Right? It is constant because it has to be. Right? But the value can actually go up and down because it's reacting over here. Right? But if we supplied a constant Dirichlet boundary condition, and so let's say that we required that the right-hand side value here would be 0, then that would stay constant, and everything else would kind of wiggle around that. Yeah. Mm-hmm. Okay. All right, and so let's go ahead and look at the next example. So the next example is really cool, and so it's I hope you guys enjoy it, because it does produce a pretty nice animation. And so for the next example, we're going to look at a case where not the boundary conditions are changing with time, but the properties in the problem are actually changing with time. And more specifically, we're going to look at a case where the convection velocities actually change with time. And so this is to basically emulate a case where, let's say that we have the wind patterns. So you're simulating something in the air, and the wind itself is changing with time. This is also a 2D case, and so the 2D will produce a very nice animation. Okay, so let me just write the whole thing down, and then we'll talk about it. All right. And so the problem here is that we have partial phi partial t plus 50 cosine pi t times partial phi partial x plus sine pi t times partial phi partial y. Okay. And that's equal to 3 times partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. And so if you notice here, the time variable is entering into our equation, and it's entering it through these terms right here. Okay. And so this 50 cosine pi t, since this is in front of partial phi partial x, this is going to be our convection velocity u. And the sine pi t, since it's in front of partial phi partial y, that's going to be our y component velocity v. Okay. All right, and so we're going to solve that equation on the following domain. And so we have a square. Ignore my inability to draw a square. All right, and so I'm going to have Dirichlet boundary conditions all around just for the sake of simplicity. Okay. And so that's the number of grid points we're going to have in the x direction, the number of grid points we're going to have in the y direction. The time step size, I'm going to set it to be 0.1. And the number of time steps we're going to solve it for is 500. Okay. All right, and what we want to do is we want to write the MATLAB code to advance the system forward in time using implicit Euler. Okay. All right. And so this is the first time that we're going to see that our convection velocity, or I'm sorry, I should maximize this. And so this is the first time that we're going to see that our convection velocities, or parameters in the problem, are actually going to change with time. And so that's actually going to change the structure of our code quite a bit. And so if you compare this code to some of the implicit Euler codes that we saw last week, and even compared to the one that we just did, this structure is going to be quite different because the velocities are going to change with every single time step. Okay. All right. And so, again, this is a problem where most of the focus is going to be on the code, but I did want to write out a few things on paper here first. Okay. Before we jump into it, are there any questions on just the setup for this problem? Okay. All right. And so, let's go ahead and since we're using implicit Euler, let's go ahead and use our formula for it. And so I think this is the first time we're going to do an example with implicit Euler in 2D. And so I basically repeated this formula for you. Okay. Okay. And so the implicit Euler method in 2D, what we have is a minus u delta t divided by 2 delta x minus k delta t divided by delta x squared. Okay. This is phi I minus 1 comma j n plus 1, right? Remember, since it's implicit Euler, we have a lot more n plus 1 terms than we do n terms. Okay. Okay. Then we have the I plus 1 term, and so the I plus 1 term is u delta t divided by 2 delta x minus k delta t over delta x squared. Okay. Then we have the j minus 1 term. Okay. Then we have the j plus 1 term. Then we have the I comma j term, and so that's the my ID. Okay. Okay. And then we have the known solution, the current solution phi I comma j at m, okay, plus our source term q I comma j. So this formula, we've seen before in the past, and actually we probably might have seen it at the end, near the beginning of class on Monday. Okay, but I did just want to write it down again, just because there's a lot of coefficients kind of floating around. Okay. All right, and just like we did in the last example, we're going to take all of the contributions from the equation, and so we're going to take the values of the convection velocity, the diffusion coefficient, the time step size, the grid spacing, all that good stuff, and we're going to plug it into this expression here. Okay, and then just like the last example, what this expression is going to give us is algebraic equations that we can apply on the various nodes in our grid. Okay. So very much just like the last example, it's just now there's just a lot more terms going on because it's 2D. Okay. But the big difference in this example is that unlike the previous example where our coefficients were constant, right? We go back to the previous, let me just scroll up the previous example really quick, right? And so in the previous example, when we formed our coefficient matrix here on the left, everything was constant. And so we could basically just compute it once and just use that matrix again. Okay. In this problem, because we have our velocities, right? Okay. Since all of these terms are changing with time, that means at every single time step, our coefficients are going to change. Okay. Okay. And so it's going to be different because we're not going to be able to just compute the coefficients ahead of time and just use them in the time stepping loop. Okay. This means that at every iteration of the time stepping loop, we have to recompute our coefficients on the fly. Okay. Okay. And so this is the main reason why I said, the structure of this code is going to be different. And so, you're going to see probably for the first time in this class, but not the last time, you're going to have a nested for loop. And so we're going to have one loop for the time, another loop to loop over the X component, and another loop to loop over the Y component, and they're all going to be inside each other. Okay. Wow, that sounds really bad. And they're all going to be nested within each other. Okay. You'll see what I mean. And so in the end, it ends up being a it's a fun code. And so you see that it's probably the most expensive code that we've run so far. And so we'll see how powerful this Podium computer is. I don't think I've ever run the code on here before, but we'll see how it does. Okay. All right. So any questions on this before we jump into the code? Okay. All right. So let's go ahead and jump in. So let me go ahead and share my screen here. Okay. And so this code is posted for you onto Canvas as well. Okay. And so and so you don't have to type anything out here. And so it's a lot of code to go through. And so I didn't want you to have to type anything. So that's why I kind of gave you just a fully worked example. Okay. Okay. And so in this example here, you can see that we're defining the variables. And so these are all, pretty standard stuff, right? You can see here that since our diffusion coefficient is constant, right? And so I'm just setting that up here. And the time step size is 0.1. And the number of time steps, I believe we set to be 500, right? So let's set this to 500 here. And so then we're also populating a coefficient matrix A as well as a right-hand side vector B. Okay. Let's see. And then before we jump into the time loop, we have to define our current solution and our next solution. Okay. And so we're setting those to be zeros for now. There's some code here. So lines 25 through 27, you don't have to worry about that because this is just producing the video. Okay. And line 30 here, is going to be our time variable. Okay. So this is very similar to the last example. Okay. And then with that, now we're ready to jump into the time loop. Okay. So remember what I said, we're going to have a loop nested within a loop, nested within a loop. Okay. And so our outermost loop here is going to be for the time loop. Okay. Because that's the thing that's going to be march us forward. That's the thing that's going to march us forward in time. Okay. And so the first thing that we're going to do inside the time loop is we're going to compute our two convection velocities, right? So remember from our problem, our x convection velocity was 50 times cosine of pi t. And so that's what we have there. And our y velocity is sine of pi t, okay? And so because these are sinusoid functions that depend on t, the values of u and v are going to be different in every time steps. And so that's why we compute their values inside the time loop, because each time the loop, comes back up, these are going to have a different value. So we need to make sure that we recompute these, at the beginning of each loop. Okay. Okay. And after we've done that, so once the value of u and the value of v are defined, then we jump into the spatial loops. Okay. And so just like we normally do in 2D problems, we loop over I and j, and we're going to set the values of the coefficients, based on those locations. Okay. And so just like every 2D problem, we're going to compute the ID numbers. And so we have my ID, left ID, right ID, up ID, down ID. Okay. And then we're going to set the coefficients. Okay. And so this is why I gave you kind of a general implicit Euler in 2D formula back in your notes, right? And so what you can do is you can match up the values of these coefficients along with your, along with the formula that you have. Okay. And so let's take the left node, for instance, right? And so this is I minus 1 n plus 1. Okay. And so you can see here we have a minus u delta t divided by 2 delta x minus k delta t divided by delta x squared. Okay. And so if you look at this formula here and you look at your notes compared, you should have the same values for for this and that. Okay. And then after that, we also have to set our source function. And so our source function here is 3 times x times y. Okay. Let me remove that 0 there. Okay. And so I think for the original thing, I turned it off. And you'll notice here that I'm also including the sole cur at my ID. Okay. And so for all the interior nodes, remember we have to add together, or we have to add in the solution at the known time step. Right? And so that's why we have sole cur at my ID here. Okay. So don't forget this. And so I think this is the part that I think a lot of people forget when they first are writing these codes, is that remember, when you're doing an implicit Euler, then the current solution has to be on the right-hand side forcing vector in some way. Okay. And this is the part that does that. Okay. Any questions on this so far? Okay. All right. And so once we've set the coefficients for all of the interior nodes, we can also apply our boundary conditions. And so these are very straightforward boundary condition loops. And so you can see here we're setting a Dirichlet boundary condition with the value of 50 on the left side, a Dirichlet boundary condition with the value of 50 on the top, a Dirichlet boundary condition with the value of 25 on the right, and 25 on the bottom. Okay. And then once the coefficients of A and B are satisfied or specified, then we can go ahead and invert the system. So we have the next solution is equal to A backslash B. Okay. And then after we solve for the solution to the next one, then we just update the current solution. Okay. So that's pretty standard. Okay. But again, the big difference here is that for for all of the nodes, we usually set these coefficients before we jump into the time loop, but because the coefficients are changing with time, we have to update their values at every loop. Okay. All right, and the rest of this code, this has to do with plotting, and just like we saw in the first example today, we have to update our time variable. Okay, we have to make sure we have t is equal to t plus delta t at the end of the time loop. This last line here just closes up the video. So let me go ahead and run this and hope that the podium computer doesn't explode. Okay. Right. Oh, it's doing pretty well. Okay. So you can see, kind of the result of the simulation. And so because the velocities are changing with time, remember the x velocities are changing between forward and backwards, you get this kind of undulating kind of membrane here. Okay. And so what's happening is that, I designed this in a way where, the boundaries on the left and the top, they have a certain value. And so when the velocities are pushing to the right, then it's going to push those values out towards the middle of the domain. So that's what you see when you see the red or the yellow membrane kind of push forward. Okay. But when the velocities are pushing to the left, it's going to push the boundary conditions on the left and the bottom towards the middle of the domain. Okay. And so that's what you see when the membrane kind of retreats back up there. Okay. And so it's a little bit choppy right now because because it's kind of solving every step. I remember I said that this process is pretty slow. Okay. But once this is done, then I'll play you the full video. Yeah. Yeah, it looks pretty cool. I think this is why I set the number of time steps to 100, because otherwise it takes a while to run the simulation. Should be done any second now. Unfortunately, I don't have any progress markers here. And so usually for a longer code like this, that's going to run for a few minutes, I like to put some progress markers just to see, where it's going. But unfortunately, I didn't do that. And so, we're just going to have to wait for it to finish. And unfortunately, it doesn't produce the video until it's done running. Okay. But I guess while that's running, are there any questions on this code?
So for this animation, it's just showing like the equation itself fluctuating.
Exactly.
The boundaries, that's it.
Exactly.
How does this apply to the real world?
Yeah. And so this could be used for a case where you have, wind patterns that kind of change back and forth. And so if you think of the colors here as kind of representing, concentration of like a pollutant or something, then if you have, maybe like a tornado or something where like the velocity are changing kind of rapidly back and forth, then you can see how, the concentration of the pollutant would, change with time. Yeah. And so you'll have times when, the pollutant is kind of flooding the domain, like, when it's going on the forward case like this, and then times when it's, when it retreats back, when the velocity pushes the other way. Okay. I guess another good example of this would be like the tides. And so if you think of like the tides at the beach, right? So those kind of ebb and flow. And so this kind of represents the same thing as well. Okay. All right, question. So is this code similar to what we will code for the project? Yes, it is actually. And so the project, I'm gonna announce this at the end of class, but I'm gonna be working on your guys' project specs next week, because I do want to get those out to you before the spring break so you can start thinking about them. But basically for the project, you are going to be simulating something like this. So some kind of unsteady time-dependent phenomenon with both convection, diffusion, source terms, and all that stuff. What exactly you guys will be simulating, I'm still deciding, but I'll have the specs ready for you by next week. Okay, so the video is done finally. So let's go ahead and view it. Okay, it's a lot cooler when you view it at full speed. Okay. If you move your mouse with it, it looks like it's following the mouse, but it's actually not following the mouse. Okay. So this is, I think it's pretty cool because it's, this is the part where you can actually make animations, and because you have kind of full control. You have full control of like the time step size and everything like that. You can make this as smooth or as janky as you want. Okay. And so if you really want, and try this at home, don't do it right now because it's going to make your computer really slow. You can increase the resolution on this as well. And so instead of 30 by 30, you can make it 100 by 100. and you'll end up with a much smoother plot. Okay. You can make the time step size a lot smaller too. So you can make this like 0.01 seconds. Okay. So don't try it now. Try it at home. Probably if I do it, if I do it here, it's probably gonna crash Zoom. But it's a fun thing to try. Make sure you have like an hour to wait as well. Maybe do it, while you're eating dinner or something. Okay. So let's go ahead and bring it back.
Was there somewhere in the setup that tells you how many times it's going to go back and forth?
Yeah, so that depends on your time step size, and it depends on how many time steps that you run. And so it's gonna make a full cycle based on the cosine terms, right? And so if we come up here, right, our terms are cosine and sine, and so it's gonna make a full cycle forward and back basically every time the cosine kind of makes a full cycle as well. And so because I have this pi here, it's going to cycle, every 1 second, it's going to cycle back and forth. Yeah, and so you can manipulate dt, and you can manipulate the number of time steps to make it cycle back and forth as many times as you want. Yeah. Let me just double check that I got everything here. Okay. All right, and so I think that's everything. Okay, so that's everything with finite differences. And so we're done. We're all done with finite differences. And so technically speaking, if I gave you the final project right now and you wanted to do it in finite differences, you have everything that you need. So you have in some sense you can say that the class is kind of done at this point. But it's not really done. We have the other half of the class, which is the finite volume method. And so for the finite volume method, you'll see us kind of revisit a lot of the same topics that we've gone over in finite differences. It's just that we're doing it in a slightly different way. And so maybe not so interesting to you guys, but when I took over this class, someone it was taught previously before. The previous instructor only really focused on the finite volume method, and so they really dived deep on that. I think the finite volume method is really cool, but from a mathematical perspective, you'll see it's a little bit more complicated to set up than finite differences. And so I think what tends to happen, because I had a class like that too. So I had a class where I just learned finite volumes, is that a lot of the kind of the purposes and kind of the big goals of why we're doing this kind of get lost in the weeds with finite volume, because the math behind this is a little bit more complicated. So I'd like to start with finite differences because it is a little bit more simple to kind of get rolling. And then once you kind of understand everything with finite differences, it makes finite volumes a lot easier to understand. Okay. But this whole time, just remember to think of finite volumes as just kind of a different way to approach these problems as finite differences. Okay. All right. So with that said, let's go ahead and introduce finite volumes first. Okay. And so let's start by saying, up until this point, we've worked on the finite difference method, where we worked kind of directly with the differential equation. Okay. And so what do I mean by that? And so, for finite differences, we had a situation like this, right? We had our differential equation. Okay. And when we applied finite differences, okay, so I'll call that FD, we took these derivatives and we directly transformed them. Okay. So we have phi I plus 1, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j, divided by delta x squared, and so on. Okay. And so in other words, what you can say is that the the derivatives themselves were being directly discretized. Okay. Another feature of our finite difference method is that once we obtained our finite difference equation, we applied them onto the points or onto the grid points or onto the nodes of our mesh. Okay. And so when we made a grid, right? Okay. And so here's kind of an example grid. Our focus on for finite differences was on the points, right? And so we label the points. Right? I'm not going to label all of them, but you get the point, right? And when we solved our solution, we were solving for the solution values at these points, okay? And so the points were the focus. Okay. I bring these up, because basically finite volumes is going to look at these in a little bit different way, okay? And so what you'll see is the finite volume method is going to change the way that we discretize the equation. And so unlike working directly with the derivatives, we're going to do something a little bit different, okay? And instead of working on the points, what we're going to work on instead are the cells, okay? And so if you have kind of a checkerboard pattern like this, right, you can look at it in terms of the points, but another way to look at it is as a collection of cells, right? Okay. And so the finite volume method, we're going to focus our attention on the cells instead of the points, okay? And because of that, it kind of leads us to slightly different mathematics. Okay. All right. So that's a little bit of a preview of what's going to be different with finite volumes, let's talk about some of the more prominent methods out there. Okay, and so probably the ones that you're going to be most familiar with, in terms of computational methods. Okay. What you'll notice is that they all start with finite, right? Okay. There's finite difference. There's finite volumes. And another one that you might be familiar with, I know some of you are because you were literally in that class last semester, is finite element. This is kind of the big three of finite methods that are out there. Okay. All right. And so of course, we've gone over finite difference. Okay. And so we know how that one works. Finite element, we're not going to go over in this class, but if you are interested, there's EGME 410 if you're still around next year. Okay. So we're not going to cover that in this class. But for the rest of the class, we're going to focus on the finite volume method. Okay. And so you might be wondering, why are there so many different methods for solving, essentially the same problem, right? And so so far I've kind of introduced this finite volume method that, even though it approaches it a different way, essentially we're solving the same thing. So why do we need so many different methods that do the same thing? So the real answer to that question is that there's a lot of scientists over the years that wanted to become famous, and so they all came up with their own methods. And scientists, you'll probably already, are very egotistical people, and so they have to claim credit for something, and so they come up with a different way to solve the same problem, and then they get to claim credit for it and become famous. And so that's part of the reason. But the more practical reason is that each of these methods kind of have applications where they really excel. Okay. Okay. All right. And so, for example, if you think of the finite element method, the finite element method really excels in structural problems. So if you're solving for, structural stresses or displacements or something in a solid structure, finite elements is great for that. And, I think it's pretty much industry standard at this point. Okay. Finite volumes, on the other hand, are really great for any kind of transport phenomenon. And so when you talk about thermofluids, finite volumes is probably the industry standard for that, because it has a lot of nice properties that make it, really nice for those. Okay. Finite difference. Unfortunately, I not that I've seen a lot, is not used a lot in industry, but I would say where finite difference's biggest strength is as an educational tool. Okay. And so when you're first kind of learning about these computational methods and you're first learning how to implement them, kind of like your first MATLAB program, your first Python, personally, I think it's the easiest to get started with finite differences. That's kind of the first one that I learned, and like a lot of my other intuition is kind of based on what I learned from finite differences. Okay. I have heard that finite differences is used for like electromagnetic applications, but I don't really have that much experience with that. But but outside of that, the only really application that I see is for education. But I think that's an important one, right? It's really the first method that everyone learns, and so I think that's really nice. Okay. But finite volume, coming back to finite volumes, it's really important to learn, because this is what people use to actually simulate heat transfer and fluid phenomena. Okay. Okay. And if you're familiar, with some of the open source projects, and so you might have heard of a code base called OpenFOAM. And so OpenFOAM uses the finite volume method, and so that's their method of choice. Okay. And so I'm actually hoping that by the end of the class I can do a little bit of introduction to OpenFOAM, but it's going to depend on how much time that we have by the end. Okay. Any questions on this so far?
So does that mean you could use any of the methods to solve the problem? It's just going to be more challenging that way?
Yep. Actually, finite elements is interesting, because a lot of my own work, I do a lot of CFD, with my own research and my own professional work, but I do finite elements for CFD, and there's certain advantages for that too. But finite volumes is used a lot for CFD because it's perfectly mass conserving, and so what you'll see is that you'll always satisfy conservation of mass no matter what with finite volumes. If you use finite difference in finite elements, the conservation of mass is satisfied, but it's done so in what we call like a weak fashion, and so you're not guaranteed to satisfy conservation of mass. And so in certain situations, you might have like more mass coming in than you do leaving a geometry with finite elements, unless you're kind of very careful with your mesh and stuff like that. And so with finite volumes, you never have to worry about that, and so that's why a lot of people tend to use it for that. But there are other advantages to the other methods that kind of take a little bit too long to kind of discuss it. But yeah, but there's overlap for sure. But the preferred, if I would say the most preferred method for CFD is definitely finite volumes. Yeah. Mm-hmm. Okay. All right. So let's go ahead and continue. Okay. All right. And so no matter what method that you choose, finite difference, finite volume, finite element, the goal is the same, right? And so the goal for any kind of finite method is to take a differential equation and turn it into a set of algebraic equations. Okay. right? So no matter what method you choose, that's always going to be the result. Okay, it's just how you obtain that. How you obtain that is going to be how you obtain those algebraic equations is going to be different. Okay, and the mathematics can be very different between the methods as well. You'll see very soon once we get into finite volumes. But like I mentioned before, the big difference with the finite volume method is that we're going to be focusing on the empty spaces in our grid, or in other words, the cells. Okay. And so I've already shown you kind of what it looks like in 2D, but that concept applies in 1D as well. Okay. All right, so here's a typical kind of mesh or grid in 1D, right? And so we have, in this case, 5 different points along the line. And so usually, when we look at something like this, we're going to say, okay, we're going to solve for the solution at each of the points, okay? And we're going to use finite differences to get that. Instead, another way that you can look at it is that instead of looking at it as a collection of 5 points, you could think of it as a collection of 4 line segments that are connected together, okay? And so this segment here in between, these 2 nodes, this is like our cell, okay? And I'll use the term cell a lot, because we're not actually going to be doing any problems in 3D, because that would be kind of way too expensive. And so I know technically the word volume, you think of like a 3-dimensional object, but even though we're using it a finite volume method, you can apply that same concept to 1D and 2D. It's just that your concept of what constitutes a volume or what constitutes a cell is different in those regimes. Okay, and so I'll use the term cell a lot more often rather than volume because I think that's a little bit less confusing. Okay. All right. And so because we're focusing on, not on discrete points, but, on finite regions, okay? This kind of opens up the door for other kinds of mathematical tools that we can use, okay? And in particular, what's one mathematical tool that you can think of that kind of solves an equation over a region of space, right? And so one tool that comes to mind is integration. Right? Okay. And so let's say that, we'll call this x1, x2, x3, x4, x5, right? And so those are the x coordinates of all the grid points. And so what if we take our equation, okay? And so let me do this. And we said that this dot, dot, dot here, this is our governing differential equation. Normally what we do with that governing differential equation is that we discretize it directly. But what if we did this instead? And so what if we take our governing equation and integrate it? Okay. And of course, you might be asking, why in the world do we want to do that? Right? So differential equations are already difficult to solve. Why would we bother with the integration? Well, with the integration here, it kind of turns the problem into something a little bit different, okay? And so it changes kind of the mathematical properties of our solution. So, just like we just discussed, just like 5 minutes ago, one thing that's really nice about this is that it becomes perfectly mass conserving, okay? And so let me draw an analogy to something that you might be familiar with, or maybe you're not, maybe you don't recognize it because it's a suppressed memory, but I know everyone has seen this before, okay? And so think back to your fluid mechanics class. Okay. Think back to your fluid mechanics class. And so does the term control volume analysis ring any bells? It should for you. You were in my fluids class. But that was 2 years ago. I understand. Right. And so if you remember from fluids class, if we, if you wanted to perform, conservation of mass, conservation of momentum for a fluid inside a device, okay, then one thing you could do is you can draw a control volume, okay, around whatever structure that you're analyzing, okay, and then from that structure, what you applied was basically an integral equation, right? Now, if you remember this, that would be really something. This might be a true suppressed memory for one of you, right? Right, and so if you remember, the way that we applied control volume analysis was we applied what was known as Reynolds transport theorem, or RTT, okay? And, through that equation, through the fact that it is an integral equation, what we could say was that, we could have things like mass conservation. Okay? Momentum conservation. Okay? Energy conservation. What we did was we used that Reynolds transport theorem to formulate all of these ideas of mass, momentum, energy conservation in integral form. Okay, and because of the mathematical properties of the integral, we can make those expressions. So we can say that mass is being conserved if we integrate over this entire region. Okay, and so the beginning motivations, or the people that developed finite volumes, kind of developed it with this in mind, okay? And so they said, control volume analysis in fluids, it has a lot of really nice properties that we want to include into our computational solutions. And so can we form a computational method that kind of takes a lot of these same properties, and what they came up with was the finite volume method. Okay. All right, any questions on this?
Yeah, I guess how would that kind of translate into like what we're doing, like in like that? How are we conserving mass like numerically? I guess.
Yeah. Yeah. No. So the kind of the reason we're conserving mass is that we're integrating our governing equations over the entire cell, and we're forming that into algebraic equations that relate to each other from cell to cell. And so, what it'll make a lot more sense once we actually get into the details. But, what we're going to do is we're essentially going to take our cell here, and we're going to form another cell over here, right? Right. And so by integrating the solution over the cell, what we're going to get essentially is that, whatever leaves this cell, by convection or diffusion or whatever, that exact same amount has to enter this cell as well. And so we have this kind of perfect balance where, like, we have something leave one cell, it has to enter another cell, and they have to be numerically identical because of how we form the integrals.
Kind of also shows like equal spacing.
Exactly. Yes. Yeah. And that certainly helps as well. Yeah. Okay. All right. Let me just go over one last thing because we only have 5 more minutes. Okay. And so because we're working with integrals now, the derivations and the math are going to get a little bit more complicated than finite difference. And so we're going to need to pull out some integral theorems as well. Okay. And so one integral theorem is the divergence theorem, which probably might also be a suppressed memory from physics or math or something like that. Okay. All right. And so you might have, learned divergence theorem from when you learned electromagnetism in physics or something like that, right? But I remember when I first learned it, I had no idea what the significance of the divergence theorem was. It wasn't until I took a class like this that I understood, why we're doing this. And so, divergence theorem is really useful in that it allows us to transform certain integrals into other forms of integrals. Okay, that's kind of the biggest upshot that I can give. Okay. And so let me give you an example in 2D. Okay, so I'll give you the example in 2D, and then we'll call it for this week. Okay. And so in 2D, you might have a situation like this, right? And so if you have a 2D space, you can do a double integral that covers that entire space. Okay. Okay. And so if I were to draw this graphically, it might look something like this. And so let's say that we have a square. Okay. The double integral, let's say that we integrate from, left to right and then down to up. Okay. This is going to be an integral that covers this entire region right here. Okay. Because that's what the double integrals do. So the double integrals integrate over, over one dimension and then over the other. So x and then y in this case. Okay. Through the divergence theorem, what we can say is that this integral here is going to be equal to a line integral. Okay. And so this right here is a line integral around the boundary. Okay. And so these are two fundamentally different integrals. And so instead of integrating over the entire 2D region, what we're doing instead is we're only doing an integral around the outside, around the outside, around the outside. Okay. And so in other words, it turns a region integral into a boundary. And so this is a tool that we're going to use, a lot in our finite volume derivations in order to get boundary integrals. And those boundary integrals are going to supply basically, that condition that we just talked about, where, something leaving one boundary has to enter another boundary. And that's how things are enforced in finite volumes. Okay. Any final questions on this before we wrap it up for the week? Yeah.
So will we focus on 3D? Because that's like part of volume.
No, so we're going to focus on 2D. And so 3D, a lot of the techniques that we'll go over, they extend to 3D, but mathematically and computationally, they're just kind of too expensive for us to do, in this class. But they do, the same ideas extend to 3D. It's just, mathematically becomes a little bit too much. All right, any final questions? Okay, all right, so that's all for this week. And so if you're here and you didn't get a chance to pick up your exams, I have them here, okay? And so thank you everyone for tuning in today. Hope you guys enjoy your weekend, and I'll see you guys next week. Yeah.
Just go back to the for the finite volumes and differences.
Yep.
So you mentioned like different applications. So because from the cell, we're kind of like already picturing or simulating that region.
Yep.
But for the differences, we're simulating kind of like the regions at the node. So then that kind of like simulates the inner portion of that, right?
Yeah, so it's, you eventually, if you interpolate, you can get a solution everywhere. But for the finite differences, what we actually solve for, all the different phi values, like phi1, phi2, they were at the nodes in the grid.
Oh, I see.
So for finite volumes, what you'll see is that we kind of ignore the nodes, and we actually solve for the value at the centers of the cells. and then we solve it from there. And so it's a little bit different. And so you consider cells versus volumes. If you refine the grid enough, you won't notice the difference between them. But mathematically, how we form the equation, it's going to be.
So for applications, would it be best to do volumes, like for instance, for larger bodies of fluids, or like if you have one fluid going through one like configuration or something, and then for differences like a mixture to like simulate like possibly different, that could be a different mixture, that could be different mixture, and stuff like that.
I'd say probably for both of those, finite volumes probably give you a little bit better results. But again, if you refine the grid enough, all the methods work well.
Right.
But anything that involves like fluids or transport, I would say finite volumes gives you a little bit more. It's not that it's better; it's just more bang for your buck. And so for a certain amount of computational power, you just get a better quality result.
Right.
And so that's what finite volumes are.
And it's also too that we couldn't really simulate or numerically simulate that like complexity of like two different fluids mixing together and stuff like that.
Yeah.
So that we'd also have like that error between like reality.
Exactly.
Okay. Yeah. Okay. Cool. Thanks.
Yep. You have a question?
Oh, no, I was just, you weren't kidding about how long that simulation.
Yeah, I told you. Start it when you have some spare time.
Yeah.
But it is cool once you get the whole thing working.
That was a cool lesson.
Josh, any final questions before I wrap it up? Okay, all right. So I'm gonna go ahead and close then. See you next week.